Hi everyone. I will make introductions in two languages today. First in Turkish and then I'll switch into English. So please stay with us if you don't know Turkish. Merhaba herkese. Öncelikle DNS Capacity Building Webinars serisinin 3. haftasına hoş geldiniz. Bu hafta sonuncu haftamız. İlk 2 haftalarda hatırlayacağınız üzere sizlere ICANN anlatmaya çalıştık. DNS'in temel yapı taşlarından bahsettik, DNS abuse'dan bahsettik ve bugün son olarak DNS security yani DNS güvenliği konusunu ele alacağız. ICANN'den meslektaşım Paul Moschen, ICANN teknik uzmanlarından bugün bize yardımcı olacak. Tabii bu eğitimlerdeki temel amacımız Türkiye'de DNS alanındaki uzmanlığı ve teknik kapasiteyi geliştirebilmek. Dolayısıyla bu konularda ilgileniyorsanız bu tarz eğitimlerimiz her zaman devam ediyor. IEEE ile başlattığımız bu seri IEEE Computer Society'nin de yardımıyla sizlere ulaşmış oldu. Öncelikle onlara da bunun için ayrıca teşekkür etmek isterim. Şimdi introduction'ı İngilizce olarak devam edeceğim. Hi everyone, welcome to the third session of DNS Capacity Building, DNS Capacity Development Trainings. As you see, this is our last session, and today we will talk about DNS security. But just to recap of the previous week, in the first week we talked about the very basics of DNS, and also I briefly explained what is ICANN, how it, what is its role in DNS ecosystem. And in the second week, my colleague Yazid Akanyo from ICANN Technology Office explained us how DNS has been abused and what are the mitigation strategies to tackle those attacks or threats. And in this week, we would like to talk about DNS security, which we found it very crucial for the operation, for the stability and security of internet. So if you happen to join the previous sessions, these sessions will be a complimentary, and we would like to have the sessions right after the DNS abuse to understand how we can avoid those activities on DNS. As I mentioned before, we aim to increase technical capacity and technical knowledge in Turkey for everyone who would like to, specialize in those areas. And as an ICANN, we will continue our trainings and capacity building webinars in those topics. If you are interested in having further trainings or joining hands-on sessions or workshops, please get in touch with us. Without further ado, today we have our colleague Paul Moschen. Paul, welcome and thank you for being with us. This is our last session. And I would like to leave the floor over to you. Thank you.
Thank you very much, Seher, and a very warm welcome to everyone in our final session on DNS. And today's topic, we're going to talk about DNSSEC and why it's important to understand it. And as Seher, just go to the next slide. Our agenda is actually as follows. I'm going to walk you through an overview quickly for the DNS, for those of you who perhaps were not in a position to join us in the first webinar. And then I'll give an introduction of DNSSEC, what it is, and what it adds to the DNS, and what does it solve and what it does not solve. Then I will talk a bit about cryptography and the basics of it. The reason we look at cryptography is because DNSSEC heavily borrows cryptographic primitives in order to secure the DNS data. And we'll have to look at what these cryptographic primitives are. I will try my best to break down the very high technical descriptions into concepts you'll understand. And then the next thing, we're going to look deeper into DNSSEC. What does it add besides cryptography? DNSSEC is very, very interesting. It adds some new records, and it also has certain operational considerations you have to think about when you're actually deploying DNSSEC. Then we look at also these new records. What does DNSSEC resource records look like? and we'll give a description of what their functions are. And I'll do this at a very high level. I will actually simplify it such that you'll be able to grasp quickly on what these resource records actually do. We look at the other part of DNSSEC, which is validation. There are two parts to DNSSEC. There's the signing and there's the validation, and they are each important. We look at DNSSEC validation, and we're going to actually look at currently, this is how DNSSEC has been deployed globally. And we look at specifically in Turkey, the case of DNSSEC validation in Turkey. And I will mention briefly about resolver considerations, but I've actually changed the order of the agenda. So I'll talk about DNSSEC considerations as part of DNSSEC validation. So let's go to the next slide. I ask of you, as usual, to ask questions and answers. Feel free to post your questions and answers on or even suggestions on the chat or on YouTube, and either my colleagues, Yazid or Seher, and I will be able to actually read them out and also answer them in the course of the webinar. So without much ado, I just want to mention briefly what the DNS is. In my first webinar, I talked about the namespace, and I mentioned that the namespace can be thought of as a tree. And in graph theory, a tree is actually a graph without any cycles, it's called an acyclic graph. And usually how it is arranged is you have the root node, which is the very top node in the tree, and beneath that you have subsequent nodes known as that are distant from the root, with the ones that are closest to the root known as top level nodes, and the next layer is the second level nodes, going down the tree up to n level nodes. And if you look carefully at the top level nodes, you have now the top level domains such as .tr, .com, .coffee. And the second level nodes are the nodes in which now you have second level domains. And these are the ones that you interact with directly with your registrar, such as example.com, mail.example.com, and so on. So this is how the DNS is actually structured globally. Next slide, please. And we talked about basically how the DNS resolution process works. I gave an example that if you have a website and you wanted to access it, your device, first of all, does actually send a query to what you know as a stub resolver. Stub resolver is a software within your iPhone, your Android device, your mobile, your laptop, or even your desktop. And if the answer of maybe the DNS response, and in this case, the query that you're making is you want the IP address of maybe a service known as example.com. If, for example, the IP address is not stored in a stub resolver, the next place where the query will be sent is now the recursive name server. And I mentioned the recursive name server is actually a piece of infrastructure that is actually in the ISP, or it could be globally provided as a service known as an open resolver by the likes as Google's 8.8.8.8 or Cloudflare's 1.1.1.1. And once the query reaches a recursive resolver, it then performs a sequence of what I can call it, it gets a sequence of referrals by sending the query to the root server, asking the question, do you have the IP address of example.com? The root server gives it a referral that it does not have, but it does know the addresses of .com. And then after that, it will then ask the same question to the .com authoritative name servers. Do you have the IP address of example.com? .com name servers then tell the recursive resolver to actually check out that it does have details, the name server IP address of example.com, and therefore this is IP address. So then it sends eventually to the name server of example.com asking for the IP address of www.example.com or just example.com. And then it receives that response and stores it in its cache. and gives now and then it sends now the answer to the device. So this is how the DNS resolution works in a sequence of recursions, and in each recursion there is actually you can say a referral is given by each and every level or name server within either the root zone or the .com zone or the example.com zone. Next slide. And we looked at also in last week's webinar, my colleague Yazid walked you through this diagram, and he looked at some potential targets of the DNS ecosystem that are susceptible to attack. We mentioned there are quite a number of ways that DNS is susceptible to attack, from man-in-the-middle attack to cache poisoning or data modification, to spoofing of data, and even the corruption or data corruption. And we're going to look at a specific attack which is addressed by the DNSSEC. And next slide. So DNSSEC actually comes in the following, and it's good to you understand the nature of this attack. So this is an insidious attack. We talked about the DNS resolution process. The question is this: supposing I actually was querying maybe whatsapp.com or example.com, for example, the resolver is going to perform a sequence of recursions and it'll get referrals. But how do we know that the answer that we've received is actually the correct IP address of whatsapp.com or example.com? There's really no way of knowing, because what could happen is before the recursive resolver gets the responses from the different authoritative name servers, an attacker can inject their own response into the cache of the resolver. And so if, for example, the IP address was maybe designated 1.2.3.4, the attacker could actually inject their own maybe 2.3.4.5 into the resolver. And therefore, in this case here, the answer is then spoofed. So if the answer is spoofed, we now call this form of attack known as cache poisoning attack, because the attacker has injected directly before the actual or correct response has been received by the resolver directly their own answer into the cache of the resolver. And this actually was, the cache poisoning attack was demonstrated in 2008 by the late Dan Kaminsky, and he showed how it is easy to compromise a resolver and send, can I say, falsified DNS data onto the resolver. Next slide. So the question is this: how do you protect against this kind of attack? And this is where DNSSEC comes in. And I'm going to talk briefly on DNSSEC and how it came about. So next slide. So DNSSEC is a protocol. It's actually an extension. It's known as the domain name security extension. So it is built on top of now plain DNS. And what does it do? The DNSSEC adds security to the DNS by using public key cryptography, which we'll talk about. And it does this in order to protect DNS data from actually spoofing, and also from actually, it actually protects the integrity of DNS data. And DNSSEC has been developed over a course of nearly 2 decades, but the documents that, can I say, the foundational documents for which you'll actually, which describe the specification of DNSSEC are requests for comments, or RFCs, 4033, 4034, 4035, and there's also one more, 5155, 5155. Those are the foundational documents that specify what this protocol is, how it operates, and what it's supposed to do to DNS data. Next slide. So this is just a quick overview of the timeline. So discussions on actually improving the security of the DNS began as early as 1993. But it wasn't until 2005 that through various efforts within the Internet Engineering Task Force, that the actual standards were actually published. So the documents I mentioned in the previous slide, 40, 33, 34, and 35 were actually published in 2005. Since then, a lot has happened. So one, in July 2010, ICANN signed the root zone with DNSSEC. By 2011, .com was actually one of the first top-level domains to sign their zones. As of today, in 2021, all generic top-level domains have been signed. The only ones that have not totally been signed are now the country code top-level domains. And in 2018, we did, as ICANN, our first root zone KSK rollover. I'll explain what KSK is. Next slide. So DNSSEC adds security, but it does not solve all the security problems associated with DNS. So DNS does only this. It actually uses public key cryptography to add what is known as data origin authenticity. So what is this? To break this up, data origin authenticity is, did this response? So you're actually asking for example.com or whatsapp.com and you get an answer. So how do you know that this response is actually authentic? Is it the correct one? Is it an authentic one? DNSSEC is supposed to answer our question. So did it really come from whatsapp.com? Did it really come from xyz.abc? That's what DNSSEC is asking. Then it also adds what is known as data integrity. So the question of data integrity is, was this data modified by an attacker, maybe in transit? And if it has been modified by an attacker, can we detect this? And then after that, we actually resolve to actually not serve this data. So this is a question of data integrity, that it was not modified by an attacker. So DNSSEC is supposed to actually answer these two questions. So in sum, it protects against spoofing of DNS data. Next slide. However, DNSSEC does not do the following. First, it does not provide confidentiality. So confidentiality, I'm talking about privacy. So DNS data, DNSSEC, although it uses public key encryption, you can still perform a man-in-the-middle attack between your device and the resolver, and between the resolver and the different authoritative name servers. You can still see the kind of queries you're sending and the responses you're getting. An attacker can still see that. The only thing is, it may be difficult for an attacker to modify now the data, even if they can see it. So because DNSSEC will be able to actually detect it. However, if you wanted to provide confidentiality and encryption, you want to maybe hide the queries you're sending towards from an attacker, then you'll need to use other DNS, can I say, security protocols, such as DNS over HTTPS, and you can read about it in RFC 8484, what is DNS over HTTPS, or DNS over TLS, which is described in RFC 7858. This one's actually enable you to send encrypted DNS queries between your end user device and also to the recursive resolver. Another thing also DNSSEC doesn't do is it does not address DDoS attacks. In fact, even DNSSEC makes, because of the packet sizes, since you're responding with signatures, the packet sizes are big, have actually been leveraged to launch DDoS attacks. However, in order to mitigate DDoS attacks, there's a document written by the Internet Engineering Task Force known as Best Current Practice 38. Best Current Practice 38 talks about how you can actually filter DNS queries or even packets based on the source IP addresses, and how by filtering that you can actually mitigate many of the DDoS attacks. And some of them have actually been witnessed, and I won't go into the details of that, but if you get time, check out BCP 38 as well. Next slide. So from this diagram, out of the various kinds of attacks, such as the man-in-the-middle attack, spoofing between the master and the primary master and the secondary, and also corrupted data. DNSSEC protects only from cache poisoning, which I talked about, what cache poisoning involves, and also modification of data between the name servers and the resolver. That is it. That's what you should understand about DNSSEC and the level to which it goes to protecting DNS. And next slide. So before we continue, if there are any questions, please post them on the chat, and my colleagues can interrupt me to read the questions out. But I'm going to talk about, and maybe this is something for you to think about. So how is the DNS resolution done with DNSSEC? Does something change? Okay, let's go to the next slide and we answer this question. Yes, some things do change. So I talked about the resolution process when you just send plain DNS queries and you receive answers from the authoritative name servers without any DNSSEC applied. But if you actually enable DNSSEC and you do validation on the recursive name server, we'll talk what the validation entails, and you sign now the zones, the top level domains, even the root is already signed, so the top level domains, even the second level domains, then the DNS responses you receive will have certain, can I say, flags that are added to it. So the DNS responses come with added data, and this data is actually signatures, mainly signatures generated using public key cryptography. In DNSSEC, they're known as resource record signatures, RRSig. I'll talk about them in detail. At the same time, when you're receiving a response from DNSSEC, you'll actually notice that the queries themselves come with another flag known as DO. DO means DNSSEC OK, which means DNSSEC has been activated. If the respective top level domain or the zone has already been signed. And another thing that also comes with the data is you'll get actually known as a flag. So if you have a recursive name server that's already security aware, and it is actually doing DNSSEC validation, it will also give a response to your query that it has an authenticated data, AD flag to it. But we'll go into this a bit later. So just for you to know is that whenever you actually are sending DNS queries and you receive responses, if DNSSEC is enabled, those responses also change in the sense that they have now more data added to it that consists of cryptographic signatures and other flags that prove that that your responses actually have DNSSEC have DNSSEC initiated on them. So let's go to the next slide. So this is a question of who can implement DNSSEC. So there are different players that can implement. We've talked about the top level domains and the registries. So registries are primarily one of the major, can I say, stakeholders who should be implementing DNSSEC. And in this case, the next, and for this sake, they actually sign their zones with DNSSEC. We'll talk about what signing involves and what it does. Then the others are ISPs. ISPs now, they don't do the signing, they do the validation. They configure their resolvers to validate, that is to check the signatures, the validity of signatures, as well as hosting providers do likewise. And then at the in between now the ISPs and also the registries, you have the registrars. The registrars are also candidates for applying DNSSEC. In this case, they enable their end users, the registrants, to sign their zones. And at the same time, they accept now DNSSEC records and publish them to the registries. So all these players actually are important in applying and implementing DNSSEC. Next slide. And basically, if you wanted to apply DNSSEC or deploy it, if you have the know-how or you're familiar with DNS operations and you manage your zone, you can actually apply or implement DNSSEC directly by assigning a zone. The most common DNS software such as Bind, even Unbound, Not DNS, all of those provide tools to actually sign your zone with DNSSEC. At the same time, if you're an ISP, you can actually enable validation of your resolvers. And for those perhaps who may not actually have the know-how and will need sensitization, there are various organizations, including the organization I represent, ICANN, and other stakeholders such as the Internet Society. We offer actually trainings on education on DNSSEC, and we will be happy to actually coordinate and maybe a DNSSEC workshop, an actual hands-on lab for actual stakeholders who intend to implement DNSSEC. So if you're interested in this, get in touch with Seher and we can plan one in the future. Okay, so let's go to the next slide. Okay, so now from here, we are going to delve into the technical details of DNSSEC. We are going to look at now the DNSSEC from now the first principles of cryptography, and we'll look at various what signing entails and also what validation entails, and the different resource records that DNSSEC adds. I will treat this at a very high level. I don't want you to be lost in the details because there's quite a lot of detail in this, but I want to actually simplify this as much as possible. So let's go to the next slide. I'll talk about when we talk of cryptography, what are we really talking about? So there are different schemes of cryptography. There's what is known as symmetric or cryptography, and there's asymmetric cryptography. So symmetric cryptography is you basically use one key, and it's only the secret key. You actually take a clear text and you come up with a ciphertext. So a ciphertext is an encrypted, text or message. But in asymmetric cryptography, you now have to use two keys. One key is known as the public key, and the other one is known as a private key. At the same time, there's a concept of digital signatures. We'll look at each of these separately. Next slide. Let's just start with the general idea of public and private key cryptography, which is also known as symmetric cryptography. So in this case here, what happens is if I want, let's say, to communicate to, say, Seher, and I don't want any third party, I don't want an attacker or somebody else to know what I'm communicating to Seher, what happens is on my side, or using my computer device, I generate two keys. And the software for this, the most common implementation is GPG. You can also use SSH, and there's so many other software that does this. I generate what is known as a public and a private key, and Seher does likewise using whatever software she has on her side. And what I do is the public key, I can share it with anyone. So I publish it maybe in a server, or I send it directly to Seher, or we meet somewhere and we exchange our public keys. But our private keys, we keep it secret. We keep it away. It's because that's our secret, or my secret. So I will not share it with anyone, neither will Seher. So what happens is I write a message in clear text, then I encrypt it with Seher's public key, and then I send it to her. And Seher will then decrypt it using her private key to read the message. And likewise, Seher encrypts the message, maybe a response with her public key. She sends it to me and I decrypt it with my private key. So this is the whole concept of private and public key cryptography. And in this way, the scheme is supposed to defeat a man-in-the-middle attack or somebody from actually seeing the contents of maybe of the messages that maybe we are sharing in confidence. So that's the general scheme. So the next slide. However, besides public and private key cryptography, there's another thing you should also note about cryptography generally, is that what is known as hashing. So hashing is basically taking what you know as maybe text, you can call it a text of any size. It can be in the gigabits or even a couple of kilobytes. And you come up with what you know as a sequence of bytes of a fixed size, so it has to be of a specific length, known as a digest. So many of you have come across maybe certain hash functions like symmetric hash algorithm SHA-256. So SHA-256 basically takes a text, and then it actually comes up with a digest, which is 256 characters in size. And that is what happens. So the thing with the hash is it doesn't matter the size of the data. It can be gigabits or whatever, but the end result is the digest has to be of a very fixed size. And a second property of a hash is you cannot have a digest, or you cannot have the same digest for two different kinds of text or different kinds of input data. Because if you do have the same digest for different kinds of input data, then you have you have what you call a collision. And if there's a collision detected on a hash function, then that hash function is already obsolete. It's weakened because it can be compromised. And one of the hash functions, MD5, collisions were discovered in 2004. And that is basically, there were two inputs that generated the same digest. And once this was discovered, it was actually deprecated. So MD5 is not advisable to be used on production as a hash function. So this is another thing you should understand about hashing. So I've talked about asymmetric cryptography and hashing. Now, both of them are going to be applied in digital signatures, and we'll talk about that in the next slide. So Seher, over to you, to the next slide. So a digital signature basically combines the two. It takes a hash, and then it actually takes the private to the public key. It encrypts a hash, and the product of encrypting a hash with maybe a private or public key is what known as a digital signature. So just understand the concept is basically a signature is a combination of a hash and an encryption scheme. And we're going to talk about digital signatures in practice when we talk about Dnsec validation. Next slide. So we've already talked about the background of cryptography, asymmetric cryptography, hashing, and digital signatures. How do they apply to signing a zone in DNSSEC? So I could ask you a question, but you don't need to answer. What are the resource records that are added by DNSSEC? This is just for your curiosity. But you don't need to type your answer, but we'll talk about them. Okay. Okay, so Seher has given many answers here, but the answers you've given are for plain DNS, not with DNSSEC. DNSSEC adds other records besides the ones that we talked in plain DNS. So let's go to the next slide, and I will tell you which ones it adds. So for plain DNS, we talked about this in our first webinar, that there are different resource records, such as the A, the code A, the NS, the start of authority SOA, the CNAME, which is an alias, the MX, which is a mail exchange server record, and the PTR, which is for reverse mapping, which maps an IP address to a domain name. However, DNSSEC adds more to this. It adds more records to the ones that are already associated with ordinary DNS. Let's go to the next slide. So DNSSEC actually adds the following four, you can say maybe 4.5 or 4, I'll tell you why it's 4.5. The records that are to now the ones that are already there in the DNS. So the most important one it adds is called the resource record signature. I'll talk about this, what this is. It's known as RRSig. So basically from a high level is you have a zone file, and I talk about the zone file. In the zone file, there are different records. You have your A, you have your code A, and so on and so forth. When you sign using DNSSEC, it now creates signatures of each of those records. So for the A record, anything with A record, it creates a signature. Anything with the NS record, it creates a signature. Anything with MX, it creates a signature. These signatures collectively in DNS, are known as resource record signatures. So that's what it is. That's what the RRSig is. Then what's a DNS key? The DNS key is basically a record that stores now your public key. So for DNSSEC, you generate both a public and a private key. And the public key can be shared. It's needed by resolvers. And how do you share it? You share it using a record known as a DNS key, which actually is the actual public key it's the actual public key that is in the DNS zone. Then the other thing that is there is known as a delegation signer. I'll explain what this is. This one is used actually to link a child zone to a parent zone and create what you know as a chain of trust. I'll talk about this, and I will go into slightly better description on what the delegation signer is. And the last one is known as Dnsec. So Dnsec, I also talk about it because it's needed in the event that maybe a domain name does not exist. And how are you going to actually prove it does not exist? I mentioned it is not just for its 4.5 because this what you know as Dnsec 3. Dnsec 3 is a variation of Dnsec. It does something slightly different, and I'll talk about that in other slides. Next slide, please. So basically, in DNSSEC, whenever you're signing a zone, the first step is to generate a public and a private key. And the funny thing with DNSSEC, it adds another level of complexity. You generate 2 pairs, not even one pair of, not one public and one private key, but 2. So you have one public, one private key times 2. Why is this the case? It's because it's because of operational reasons, and I'll talk about what these keys are and why there are 2 keys and not just one pair of keys. And the thing is this: when you actually when data in the zone is signed with a private key, DNSSEC allows the data to be signed ahead of time. That's another interesting thing. And usually the signing itself, the key is actually decoupled from the data. So when you sign it, you can actually keep the key separately from the data. And another thing also about DNSSEC is that what you're actually signing is not the messages. So you're not encrypting or signing the messages. You're signing the zone data. So get this, because you may confuse this. DNSSEC is signing the data in the zone file. So that is what is actually being signed, not the actual messages, not the actual queries and responses. Those are not actually the ones that are being signed or we're not applying cryptography. So that's another thing you should bear in mind. Let's go to the next slide. So another thing also is I mentioned is the DNS. When you generate a public key, you store it in a record known as a DNS key. But what do you do with the private key? The private key, you should actually keep it safely. And there are ways to actually keep the private key away from prying eyes. So you can store it in mediums such as a hardware security module. And another thing is that you can store it offline in some encrypted way so that it's only you who actually has access to that. And if you do store it online, you only store maybe the one that you need to use for the operational, the most day-to-day, functions. And this one, if you store it perhaps maybe in a secure manner, protected by you using maybe certain credentials like 2-factor authentication. So this is just another thing I wanted to mention, that when you're dealing the private key, you take extra steps to actually store it and protect it. As for the public key, you make it available to the entire world. It's fair enough. The public key, you can publish it in the DNS record and it's available to the entire world. Okay, next slide. Okay, so I mentioned something interesting about DNSSEC. DNSSEC introduces two pairs of public and private keys. So the two keys that it introduces are known as the zone signing key, ZSK, and the key signing key, KSK. Why do you need two of these? Why can't you use one? The truth is you can actually use one, but for operational reasons, you actually have two of those. This is why the KSK is actually used in rarely. You actually use the KSK rarely because the KSK is used to create a chain of trust between your zone and the parent zone. And the KSK in this case, you don't want to keep changing it. But for other things, for changing zone records, because you could maybe add more and more records to the zone. Let's say you have the .tr domain, and each time the .tr you're adding and registering new domain names, second level domain names. In this case, and you still want to maintain integrity of data, you still want to sign that data, it's best and it's better advisable that you use a zone signing key, because the zone signing key, you can change it often. You can actually update your zone each and every time you change it using the ZSK. But the KSK, you keep it separately and use this actually when you're creating a chain of trust. So for those two operational concerns, the implementers of DNSSEC decided that it's best to have two kinds of keys. One is for when you want to frequently change DNS data in the zone, and one if you rarely change and you want to create just only a chain of trust. And that is why they came up with now the key signing key and the zone signing key. Let's talk a little bit about these two keys in the following slides. So do not worry, we are halfway there. We are just halfway there. So as I mentioned, the zone signing key is used to sign now the various records in your zone file and create signatures to each of those records. So the zone signing key I've mentioned has both its private and its public component. And the public part of the zone signing key is now shared with the rest of the world in the form of a record known as a DNS key. So what the zone signing key actually does is once you actually generate it and you apply it, it'll actually create a signature and it'll create a hash of those records. So if you have an A record, if you have a quad A record, if you have an NS record, it'll create a signature associated with those records. And this record is known as a resource record signature, RRSig. That is all you need to know. So once you generate the ZSK, you apply it onto your zone file, it generates the respective signatures, which are known as RRSig, and these these signatures are then available in your zone file. They are published from your zone file, and any resolver that is doing Dnsec validation can be able to retrieve these signatures and check them. That's what you should understand about the zone signing key. Let's go to the next one on the next slide. And as I said, the public portion of the zone signing key is also published in a record known as a DNS key. That's all you need to know. So about this ZSK. So next slide. The KSK is similar to the ZSK in the how it actually works. Sorry about that. I have.
Is this your cat?
Sorry about that. I have my felines are actually making some noise, but anyway. So let's talk about the key signing key. So as I mentioned, the key signing key is actually used to create a chain of trust, and it is rarely used. But likewise, the key signing key, like the zone signing key, has two components, both the private and the public. And the thing with the key signing key is that you actually can use it to sign. So you can use the key signing key to actually add a signature to your ZSK. At the same time, you can actually use it to sign. There are some CCTLDs and even operators that use the KSK and they don't even have a ZSK to sign their zones. Likewise, it acts in a similar manner to the ZSK. You actually sign the various records in the zone file, and you come up with resource record signatures. So in a likewise manner, the KSK also can be used to generate resource record signatures, similar to the ZSK. However, it is, in the most cases, it is actually used as, can I say, as more or less to actually create a level of trust between the parent and the child zone. I'll talk about how the level of trust looks like. Next slide. So like the ZSK, the KSK has the public portion, and the public portion can be published for anyone to access it. And it's published in a record known as a Dns Key. And so the other thing I just want to mention is to differentiate between the ZSK and the KSK, they're given both identity numbers. So the ZSK in the protocols, the RFCs, is actually identified with the number 256, and the KSK is identified with the number 257. So that's how you're able to differentiate the two. Next slide. So this is now I'm going to talk about the delegation signer. This is now where the KSK actually features. So the thing is this, you can sign your zone. So you could have, let's say, .tr. You've already signed it, but the root zone and the entire world does not know you signed it. So how does the entire world get to know that you've already signed your zone? There is actually a very specific record that deals with this. It's known as the delegation signer. The delegation signer is actually a can I say it's a hash? It's a hash, just a signature, or just say a hash of the KSK, the key signing key, the private portion of the key signing key. The delegation signer is shared with the parent zone. So once, let's say, .tr signs .tr zone using the ZSK, and they publish the DNS key of both the KSK and the ZSK on the zone. .tr will then have to create the delegation signer using the key signing key and share it now with ICANN. From there, it is now possible for anybody in the entire internet to confirm the veracity of the data that is being served by .tr top-level domain, the .tr CCTLD. So this is where the delegation signer comes in, and use the KSK for this purpose. And the reason why it is it's a KSK is because you don't want to keep changing the delegation signer. The delegation signer is only changed when you actually, can I say, obsolete the KSK. So if you had a KSK, if .tr had a KSK, and they decide to do away the KSK, then also the delegation signer that they've published on ICANN will have also to be changed. And you don't want to be doing this all the time. So that's why the KSK is used for only this and this purpose alone. The delegation signer creates what you know as a chain of trust. It's used to create a chain of trust. And let's go to the next slide. And so this is how the chain of trust looks like. So we have the root zone. The root zone has been signed, and the root zone has its own KSK and ZSK. Then you have a top-level domain. It can be .com, it could be .tr, it can be any. The administrators of the .com or the .tr design their zone using the ZSK, and they also have a KSK which they generate. They then create what you know as a delegation signer, and they share it with the root zone. So the delegation signer is stored in the parent. Now, let us say I have example.com. So example.com is registered by an end user. So what happens is I sign my zone by creating both the KSK and the ZSK, and then I also create a delegation signer. And what I do is I share the delegation signer now with the .com zone. So the delegation signer is shared with the parent zone. And likewise, the chain of trust is then as follows. I want to check example.com and to verify that example.com has not been tampered, that the zone data in example.com is actually authentic. How do I do this? I actually start by getting the delegation signer from the root. I mean, from the root zone, I get what you know as a trust anchor from the root. Then I get the delegation signer from .com. And then finally, I get the delegation signer from that is already stored in the parent zone, for example.com. Then from that chain of trust, I can be able to verify all the signatures, starting from the root zone to .com, finally to example.com. And once I actually verify the sequence of signatures from the top, from the root down to example.com, then I'm able to actually give a valid, I can be able to give an answer that this zone itself is authentic or it is not. So this is what I mean by chain of trust. And when you're talking about the delegation signer, because it creates this chain of trust on the subsequent parent zones, you need the KSK for this purpose. So this is what we mean by chain of trust. So let's go to the next slide. And mention this. So one thing you should note is at ICANN, because the root zone is the topmost level domain in the entire world, and everything actually resolution starts from the root zone, there is actually an entire process for signing the root zone itself. And this process is actually done in an open and transparent manner. And it's known as the root zone, can I say key ceremony or KSK ceremony? In this case here, what happens is that they are trusted users from across the world that are selected to actually retrieve a portion of the key signing key of the root. And once they retrieve that, they then go through various processes to verify that everything is in order. And this is done, it is actually broadcasted or on YouTube or on any social media channel, such that the internet community can actually trust the root zone and that what has been signed has not been tampered with. So the chain of trust is we take it very seriously at ICANN, and it's an entire process which involves stakeholders, and they themselves also have to share their proceedings with the internet community, and the internet community has to vet that the entire process of signing the root zone or even rolling over the keys is actually done in a very open and transparent manner. So this is another thing you should note. Okay, so before I go to the next slide, I just want to ask, are there any questions so far on signing? I know it's quite a lot, it's a bit dense. The slides will be made available, will be shared with you. Usually this is the kind of background we go through before you actually do the DNSSEC laboratories or the labs, the practical signing and also validating. But if there are any questions, please let me know. Type on the chat. Are there any questions?
Hi, Paul. I'm checking the chat bot, but so far we don't have any.
All right. So I will quickly go through the various resource records. Let's go to the next slide. So basically, I'm just going to mention them in passing. I mentioned that DNSSEC adds more resource records to the DNS. And the first record we look at is the DNS key. I mentioned that the DNS key is where you store the public key. And this is actually quite, this can actually be proved. And if you look at my right-hand side, you can see some characters, some bytes, and that are on my right-hand side. So what are these? So this is how the DNS key or the public key looks like for example.com. And in this case, we are looking at the zone signing key. How do we know it's a zone signing key? Because it has the number 256. So according to DNSSEC specification, 256 is associated with the zone signing key, and 257 is the key signing key. This whole text that you see over here, all these bytes here, is the actual public portion of the zone signing key for example.com. And in the next one here, this whole text that you see here is now the public key associated with the KSK, the key signing key of example.com. So this is how the DNS key resource record looks like when you actually query for it. Next slide. So what's a resource record signature? How does it look like, for example? So in this case here, I have example.com has two IP addresses. It has a 192.0.2.1 and 192.0.2.2. A resource record signature is associated with the type, not every entry, but the type. So if you have only a record, like you have two IP addresses, IPv4 addresses, and this is known as the A record, the resource record signature will be basically a hash of this entire this entire resource record set, only the A. And this is how it looks like. It's actually a cryptographic signature, as you can see over here. And this one uses RSA. I'll not go into the different algorithms, but there are different algorithms, cryptographic algorithms that actually are that you can actually apply on DNSSEC. My colleague Yazid will share with you on the chart the different DNSSEC algorithms that can be applied, but in this case, you're using the RSA, which is a reverse Shamir-Alderman, and this is how the resource record signature looks like as a cryptographic representation of the A record. Then another thing you should note is that the signatures have a validity period. In this case here, this signature, how do you know the validity period? It is indicated by this, the first and the second fields, and this ones here are actually timestamps. So in this timestamp, this example.com is going to expire on the 17th of May 2020 at 11:55, which is 10:55 because it's 22:55, 10:55 p.m. 28 seconds. This is and it was actually activated, or it was created. This signature itself was created on the 17th of April 2020 at 10:55 p.m. 28 seconds. So usually the DNSSEC software generates these signatures and it adds timestamps. And every time the signatures are about to expire, they're actually, can I say, modern DNS software allows you to regenerate new signatures automatically. So that's how you should actually see how the resource record signatures are. Next slide. Then another signature that is Seher.
Apologies, I think there is something wrong with the document. I'm just checking it right now. Can you see it?
Yes, now we are back.
Yeah, thank you.
Okay, so the other record I mentioned, the one that's used for the trust anchor, known as the Delegation Signer, which is basically a hash of the key signing key. It looks as follows. So I'm going to skip to the fourth line. So example.com has both a KSK and a ZSK. The hash of the private portion of the KSK is known as the Delegation Signer. And the Delegation Signer can be seen over here. Just follow with me. This bytes here, 43839. This entire string over here represents the Delegation Signer. And basically, this is how the Delegation Signer looks like. It's just only a hash. And it uses a digest, so it can use symmetric hash algorithm, or symmetric hash algorithm 256 to represent it. So this is just an overview of how the delegation signer is. This is now what is shared with the parent zone. So this delegation signer is shared now with the .com zone. Let's go to the next slide. Then let's mention briefly what NSEC is. So sometimes when you are actually querying for perhaps a domain name, you may actually query a non-existent one. So maybe you may want example.com, but instead you query example1.com. So the thing is this, how can you cryptographically prove that example1.com doesn't exist? This is what the NSEC record comes in. So the NSEC is actually used to show that basically this domain name does not exist. It's used for authenticated denial of existence, and this is what the NSEC is. Go to the next slide. So the thing is that basically in the NSEC, what happens is when you see the NSEC record, it's on the domain name or in the zone file. I'm just saying the zone file. It just tells you that from this here, the next one that exists is this maybe domain. Then the next one that exists is that. So basically, I will show you in more practically how this how the NSEC looks like. Next slide. So let's have a look here. In this, I have example.com. It has the typical start of authority, the name server, the A record, which is for IPv4 address, MX, which is your mail server, can I say exchange that is there. The NSEC is as follows. If you have, let's say, multiple subdomains. So under example.com, I have East, I have FTP, I have mail.example.com, www.example.com, and I've signed them. The NSEC will tell me that the next secure, the one that exists, is east.example.com. And in it, I'll find, if I enter this zone file, I'll find an A record, a name server record, an SOA record, MX, and NSEC. Likewise, it tells me if I have another subdomain under example.com called ns.east.example.com, this also appears as the next secure one, and it tells me which records are there. If I have FTP, the NSEC will tell me that there is ftp.example.com. If I have another one, it tells me that mail.example.com is there. The next secure one after mail is ns. After ns, there is www.example.com. So using the NSEC record, you're able to tell that under the example.com, this and this and this subdomains actually exist. And if, for example, somebody typed east1 instead of east.example.com, then NSEC will tell, basically, because it references the ones that exist, that east1.example.com does not exist, and therefore it will throw an error that this is a non-existent domain. But for NSEC, it just tells me these are the ones that exist, and these are the records that are available. So let's go to the next slide. And once it has reached the end, it now goes back to the parent. So it's like it wraps around the last name, and now shows that from the very parent example.com, that's the next secure one. So that's how the NSEC works. And next slide. Okay, let's go to the next slide. That's just mentioning what I talked about. So NSEC 3 is a variation of NSEC. And NSEC 3 was supposed to prevent a problem. NSEC tells you the next secure one. So it will name the subdomain. It'll tell you that after this, there's another one and another one, and another one. It was discovered that attackers could enumerate an entire zone and discover all the subdomains for that zone. And this was actually a security problem. So the designers of DNSSEC extended it by including what you know as Next Secure 3, known as the Next Secure version 3. NSEC 3 was supposed to hide those details of the next subdomains by actually creating what you can know as hashes instead of actually you see the next subdomain, the next secure subdomain, you'll actually see a hash of that subdomain. Let me demonstrate how this looks like. Next slide. So let's just say in example.com, I have 3 subdomains. I have Alpha, Bravo, and Charlie. In NSEC, you're going to see the chain. The next secure is Alpha. Then after Alpha, there's Bravo. And after Bravo, there's Charlie. And these are all clear text. An attacker can easily see from this that they can derive the subdomains Alpha, Bravo, and Charlie from the NSEC chain. But with NSEC 3, you add a hash. So instead of seeing, let's say, bravo.example or alpha or charlie.example.com, I'll be seeing just a sequence of gibberish characters or hashes like ACGENFKS.example and so on. So NSEC 3 just hashes the subdomains so that it's very difficult to decipher or tell what subdomains are under a given zone. So in this way, you're actually adding some layer of security by masking actual subdomains from an attacker. And this is how NSEC 3 actually works. Let's go to the next slide. So this is just basically other things, including that you can opt out. So opt out basically means if you're not maybe signed, maybe there are some of the subdomains on maybe example.com haven't been signed. So those ones you can omit them from actually being part of actually the chain that NSEC will actually enumerate, or which NSEC will actually go through. So NSEC 3 allows you to omit those domains that haven't actually been signed from actually being secured. So that's basically what the opt-out is. So let's go to the next slide. I think we've almost come to the end of this one. So let me just give you an example of plain DNS, what a zone file looks like with a plain DNS, and what a zone file looks with DNSSEC. So with plain DNS, you just have your usual records. So you have your SOA, NS, the A records, MX, nothing much here. This is what we had already seen in the first webinar. But let's go to the next slide. But now when you actually add DNSSEC, now you add all this new records, such as the resource record signatures for each of those, each of those records. So if you have an SOA, there'll be a resource record signature associated with the SOA. If you have an NS record anywhere, there'll be one resource record signature associated with the NS record. If you have an A record, there'll be a signature associated with an A. If you have an MX, there'll be a signature associated with MX. If you have keys, both the ZSK and the KSK, they're published over here as Dns Key. And if you have others, such as maybe subdomains, like mail or www and others, then all of these ones here will now take the NSEC. And so this is how now your zone file will actually change when you actually apply DNSSEC. Next slide. And if you have the time, you can use the dig tool. But if you like us to do a lab, maybe to actually understand this practically, we actually have an entire exercise on using different tools to check up DNSSEC data. And the most common tool you use is dig. But if you wanted to check out DNSSEC, Yazid can share with you the link, digwebinterface.com. You can go here and just enter any domain and check out different DNSSEC resource records. Check out for the DNS key, check out for the resource record signature, check out for whether it has been signed, what algorithms it is. So you can check this out on the web and play around with it with a dig on the web. So next slide. Okay, so I'm going to briefly mention what validation is and why it is important. So next slide. So let's begin. So what I've talked so far is about DNSSEC signing, how you sign a zone. Signing is done on on the end, at the end of the name server. So when you have a name server, you're operating a zone, you have different records in that zone, then you sign. And when you sign, you use the primitives we've talked about, and you come up with different signatures and different records that now are added to the zone file. However, when you actually are doing validating, validating is done not at the name servers, but it's done now at the resolver, recursive resolver. And this is usually an exercise done by the ISP or the network operator. So DNSSEC validation is basically the process of checking the signatures of DNSSEC data, and it's done at the resolver end. And one thing you should note is that DNSSEC validation depends on the chain of trust. The chain of trust is actually very, very important for a resolver. And the root zone is by far the most important. The root zone KSK is by far the most important anchor in the chain of trust. And when validation happens, then after that, the resolver is able to verify that the data it has received is actually authentic and everything is fine. But if it fails, the resolver will then throw a self-fail error, and it will refuse to actually, it'll declare that this zone itself is actually, it cannot be authenticated. And in that case, it'll stop you from, it can prevent you from actually trusting the data or that's associated with that domain. Let's go to the next slide. So how basically this is just how validation occurs. So what happens is this: the resolver you'll ask a question to the and the resolver will receive the response from your device. Then when the resolver goes through the recursion, the resolution process I had shown in the first sequence of slides, what happens is it'll receive now the DNS Sec signed data, resource record signatures, DNS key, all that data from a given zone associated with that domain. It has to then check that that data is actually authentic. What does it do? It first of all takes the DNS key, the public portion, from the zone file, or I mean from that it has received. It then takes the data, the plain DNS data, not the encrypted part. It then generates a hash of that data, and then it signs the hash of that data with the public key. It then generates a digital signature, and then it compares this digital signature with the digitals or the resource record signatures it has received from that domain. If the two actually match, then after that, verification has taken place and everything is all right. So the idea is similar to what I'd explained earlier. You're going to actually use hashing and public key cryptography to generate a signature. And then you compare the signature that's been generated by the resolver to the resource record signatures it has received from actually querying that given domain. So that's basically the principle of actual validation. Next slide. And we talked about the chain of trust, how it's important, because the validator on the resolver is going to actually take the keys from the root. It'll take the keys from the top level domain, whether it's .com or whichever, the third level, the fourth, and so on. It'll take all those keys and it'll take all the signatures that are in those in a respective zone. It'll compare them, and if everything goes well, then verification actually happens. Otherwise, it will throw a self-fail error. Next slide. And one thing you should note is, because when you do DNSSEC validation, you're going to actually need to have some system resources to ensure that validation actually is actually conducted, because DNSSEC validation adds a bit of work to now the resolver. So it's important that your resolver has sufficient memory. That's one. Nothing is also increased CPU, can I say capacity, because DNSSEC validation and cryptography in general does take computing resources, and it's important to have much more capacity for that. Then also another thing is also network interfaces that can handle high bandwidth traffic, especially if you're a very busy resolver like a local ISP resolver. And then another thing is also you have to be able to treat large GDP packets and enable eDNS, extensible DNS onto your configuration. And other than that, also is also make sure that your firewall, you have also, can I say, sensible firewall policies that allow TCP over port 53. The reason why you're using not just UDP but TCP is because DNSSEC responses usually are pretty large packets and that are bigger than 512 bytes over UDP. And in this case here, you may want to actually enable TCP over port 53 when sending back responses. So those are some of the hardware network resource considerations you should take into account. Next slide. And the most important thing, it's very, very crucial you have accurate timing. In this case, it's important you enable the network time protocol, because the reason is because whenever you use DNSSEC and you generate signatures, the signatures, as I mentioned, do have an expiration time, then an inception time, a validity period. Those dates, those timestamps have to are reflected or generated from the time on your device, on the resolver or on the name server. So in this cases, you may want actually to ensure that the time on your name server is actually correct. Otherwise, if the signatures perhaps are incorrect, you may find that you land into problems because the signatures may have expired early because this date was set incorrectly, or they're stale. And either way, whether they expire early or they're stale, is going to cause problems. So in this case, it's very important that you do make sure that synchronization and especially NTP is working properly on your name server. Next slide. Now, this is the final part of the presentation. And we're going to, this one is less technical. And you can take a big sigh of relief. I won't talk too much about the technical details. I'll talk about the state of DNSSEC deployment currently and DNSSEC validation as well. So currently, as of November 2020, all the generic top-level domain names, the .coms, the .ninjas, and so on have actually been signed. So when it comes to GTLDs, DNSSEC deployment or signing is actually at 100%. However, the situation is quite different when it comes to country code top-level domains. Currently, it stands at 59.4% of country code top-level domains in the world are actually been signed. And the highest number of CCTLDs that have been signed are in Europe and North America. This should not be a surprise because the organizations and also the engineers within these regions deployed DNSSEC pretty early and have been experimenting with it. In Asia is also, and the Pacific is also fairly well. It's actually growing in the APAC region. But in Latin America and Africa, there's still quite a lot of work to be done to actually enable many CCTLDs to actually sign their top level, their zones with DNSSEC. Let's go to the next slide. However, when it comes to DNSSEC validation, because there are two parts to DNSSEC, there's the signing and there's validation. Validation, unfortunately, is not as, can I say, common as maybe signing and of the top level domains. Currently, worldwide, of the 3.3 million resolvers that are there on the internet, only 25% of them actually do validate DNS responses. And this is information that's publicly available on the APNIC statistics, DNSSEC statistics web portal. I'll share with you the link. My colleagues will share with you the link shortly. And it is part of our mandate as ICANN for the next 4 years to actually significantly increase the adoption of DNS Sec between the years 2021 and 2025, including convincing operators, network operators, to enable DNS Sec validation on their resolvers, at the same time working hand in hand with DNS software vendors to actually enable DNSSEC validation to be turned on automatically by default. Next slide. So currently in the world, these are just the statistics. Worldwide, it's around, this was February this year, 24.88% of resolvers in the world actually enable DNSSEC validation. In Asia, because this is the whole Asia continent, it's 23.38%, which is slightly below the world average. The highest percentage is in Oceania, and this is in the Pacific. That's at 37.97%, and the lowest is in Africa, which is at 17.59%. Next slide. In Turkey, the state of DNSSEC validation stands at 41.35%, which is above the world average, but it can still be improved. And according to stats.labs.apnic, the Atlantis Central, whose AS number is 204457, has the highest rate of DNSSEC deployment in Turkey, followed by Telkom AS and Turkcell AS at number 3. And these statistics, you can find them on the APNIC website. They are publicly available. So basically, we will work hand in hand with stakeholders, and we're happy to work with stakeholders in the region to actually enable DNSSEC on their servers. And we could actually maybe have a future, maybe a webinar just purely on DNSSEC validation and how to enable it. It's actually much easier doing DNSSEC validation than signing. Signing is a much more tedious process because there's quite a lot of steps you need to go through. But validation is pretty straightforward, and it just only involves enabling 1 or 3 lines of configuration changes on a file, and that's about it. And you're able to, your resolver is then able to do the DNSSEC validation. Okay, so we go to the next and final slide. I want to thank you so much for your kind attention and for actually attending the sequence of webinars. This reaches the end of the presentation. And if you want to engage with us, you can get in touch with either Seher or you can go to the ICANN website or follow us on any of the social media channels. So thank you so much.
Thank you very much, Paul. I have to say that you very well summarized this technical topic to the general audience. So thank you very much for this great summary and bringing this topic to our attention. As you mentioned, DNSSEC is one of the topic which takes priority in ICANN's agenda, as well as ICANN's regional plans and strategic plans. So that's why we are trying to reach out different stakeholders in Turkey and in the region. For example, we are trying to reach out the internet service providers. In 2 slides ago, you shared the list of internet service providers, and we see that the validation rate is quite low. So that's why we are trying to reaching out those people, including large network operators, including DNS providers, DNS resolver providers, and registries and registrars in the region. I believe that this training would give a better sense of how I can help those stakeholders to activate DNS security, and this training would also give a bit of sense of its importance. This is the I was checking the chat bot, and I was checking the Zoom channel as well, but we don't receive any questions so far. So I think it is the time that we can just wrap up this session. Thank you very much for your efforts, and thank you very much for your stopless breathe during the presentation, because I know that it took a lot. And I also would like to thank IEEE Computer Society, because this is our last session. And I hope that people would find it useful to understand DNS in their perspective. Would you like to add any comment before we finish this session up?
So we do offer a lab, an actual hands-on lab on DNSSEC. And if you're interested in a DNSSEC lab, SER can organize one.
Right.
Usually we organize a lab with the country code top-level domain, so the .tr registry, for example. But we welcome participation from other stakeholders, including members of the IEEE. At the same time, we also welcome participation from registrars and also end users, so that they understand what DNSSEC is. So when one is organized, hopefully Sarah will also get in touch with you, and we'll be very happy to do the DNSSEC lab. And in the DNSSEC lab, you'll actually configure your own zones. You will sign them, you will validate them, and you are going to actually do this as a hands-on training over 3 to 4 days. So we'll plan one.
Okay, thank you, Paul. And if you would allow me, I would like to just say a couple of words in Turkish and finish the session. Herkese teşekkürler katılımınız için. Bu son oturumda da DNS Security'yi konuştuk ama az önce de bahsettiğimiz gibi DNS Security'de Türkiye'de internet servis sağlayıcılarından tutun da kayıt otoritelerine, alan adı kayıt işiyle uğraşan ya da DNS Resolver işleten büyük firmalara, herkese ulaşmaya çalışıyoruz. Çünkü DNS Security bir anlamda DNS'in güvenliği için aslında uygulanması gereken işlemlerden bir tanesi. Eğer siz de bu sektördeyseniz ya da bir şekilde bu bahsettiğimiz alanlarda çalışıyorsanız lütfen bize ulaşın. Bu konularda yaptığımız laboratuvar ya daha doğrusu daha pratik eğitimler var. Hem DNS Security'yi nasıl activate edeceğinizi anlatıyoruz, hem de alan adlarının bu konuda nasıl imzalanacağı, DNS Security uzantılarıyla imzalanacağı konusunda detaylı bilgiler veriyoruz. Pratik eğitimler her zaman teorikten bir tık daha önde oluyor. YouTube kanalından bu eğitime ulaşmakla beraber mail adresimi de yazıyorum. Sosyal medya hesaplarından da bize ulaşabilirsiniz. Bir kez daha IEEE Computer Society ekibine hem yardımları için hem de bizi sizlerle buluştuğu için çok teşekkür ediyoruz. Umarım devamında daha güzel eğitimlerde, başka ortamlarda yüz yüze buluşma şansımız olur. Çok teşekkürler. Have a good rest of the day. Thank you, Paul.